Today we are going to be talking about the formation of the solar system, and this is commonly known as the nebular hypothesis. And so we're going to talk about where our solar system came from and how the different objects in our solar system were all produced. So when we take a look at our solar system, there are four characteristics of our solar system that we need to be able to explain with our theory of formation. One would be the pattern of motion that we see in the objects in our solar system. The two different types of planets that we see, we have kind of two different categories, and so we want to know why do we have those two different types and how did the formation produce that. The existence of asteroids and comets, and then also some of these little exceptions to the rule. So the things in our solar system that don't quite fit in with the other parts of our solar system. So the first thing we're going to take a look at is the pattern of motion in our solar system. And the first thing that we notice is that all of the planets orbit the sun in the same direction, and that would be counterclockwise. If we're looking down at the Earth's north pole, looking down at our solar system, they all orbit in the same direction, which is counterclockwise. There are no exceptions to that rule. Also, their orbits are nearly circular. They're technically elliptical, but most of them tend to be closer to a circle, and they're all about in the same plane, or kind of on the same level of orbit. Also, the planets rotate in the same direction in which they orbit. There are some exceptions, but that's the number 4 that we're going to take a look at. But most planets rotate counterclockwise just like they orbit counterclockwise. When we take a look at the moons in our solar system, almost all of them orbit their planets in the same direction that the planet rotates, that counterclockwise motion. And then the sun also rotates in the same motion. So we have this counterclockwise rotation and revolution throughout our solar system, so somehow that motion must have been sparked during the formation phase or even prior to that. Next, we're going to look at the two different types of planets. We have two distinct groups. There are the terrestrial planets, which are also sometimes called the inner planets, and the Jovian planets, also sometimes called the outer planets. And the terrestrial planets include Mercury, Venus, Earth, and Mars. And they are all small, rocky, abundant in metals, very, very dense, and they don't have very many moons. The Jovian planets are Jupiter, Saturn, Uranus, and Neptune, and these are very large, made of gases, not made of rocks, not made of solid materials. They do not have solid surfaces, which is why they're sometimes called gas giants. They all have rings, not just Saturn, they all have rings, and they also tend to have quite a few moons. So when we look a little more carefully at the two kinds of planets, we have the terrestrial, which you can see here, and we include our moon because we consider that a terrestrial object, even though it's not a planet. And then also the Jovian ones that you can see here that are much larger and have no solid surface. The terrestrial planets are those 4 inner ones of the inner solar system. They are pretty small in size and in mass, the Earth being the largest, and they all have a rocky surface. The Jovian planets we see here are much larger, much lower density because they're made of gases and not solid materials. And they all have rings. Remember, it's not just Saturn, they all do have rings. Saturn happens to have the largest and most extensive, but they do all have ring systems. They are mostly gas and have no solid surface. So we're going to take a look in a little bit at why we have those two categories of planets. Next, we have some other strange objects in our solar system that don't fit into the planet category. We have asteroids and comets. And asteroids are small rocky bodies that orbit in the asteroid belt between Mars and Jupiter, and we've discovered almost 9,000. And comets are small and icy that spend most of their time way beyond the orbit of Pluto, coming into the inner solar system only a few times during their lives. And we also have asteroids in the Kuiper belt and the Oort cloud, which is where we also find comets. So we want to take a look at where do these objects come from. And then the fourth thing we want to take a look at are what are the exceptions to the rules. Mercury has a larger orbital eccentricity. It's a little less circular of an orbit than the other planets. Uranus is very tilted. It's almost tilted on its side. Venus does not rotate counterclockwise. It rotates in the opposite direction. And Earth has a very large moon for being an inner planet. So we also kind of want to take a look at and think about, well, how do these 4 things that don't quite fit in, what could possibly explain those things? What could have happened during our solar system's history to cause those things? So the nebular theory is what we take a look at and how we explain the formation of the solar system. And it says that the solar system was formed from a giant swirling interstellar cloud of gas and dust. And this hypothesis was originally suggested back in the 1700s. A nebula is a cloud of gas and dust. And so that's where we get the nebula hypothesis. So please take a second to write down the definition of a nebula. The collapsed piece of cloud that formed our own solar system we call the solar nebula. So a nebula is any cloud of gas and dust. The solar nebula is the one that formed our solar system. So 3 important things gave form to our system when it started collapsing. So we had this giant swirling cloud of gas and dust, and then it started to collapse. And we'll talk later in class about what might have caused that collapse. There's a few different ideas out there. So what happened as the collapse started happening is that the temperature increased, the rotation rate of the disk increased, and it flattened. So those 3 things are very, very important. So it flattened, started spinning faster, and started heating up. And here we see a nice little picture. You can see in A here we have just a nice our solar nebula, and in B it starts to flatten, and you can't see the motion, but it would also be spinning and the temperature's increasing. You see at the center our sun forms, and then the other materials form until we get our planets forming there. So now let's talk about planet building and the processes involved in that. So we know that we started out with a solar nebula, it collapses and it starts spinning. And that spinning should kind of start to sound familiar to you. Remember we talked about the motion in our solar system is the orbit is counterclockwise for everything, and most things rotate counterclockwise. So where did they get that original motion? They got it from the spinning of that solar nebula. So the initial composition of the solar nebula is mostly hydrogen and helium and only a tiny, tiny bit of heavier elements. So the first process that started happening it's called condensation, and this is when those gaseous particles start forming into solids. They start condensating, and that word should be a little familiar to you, right? We know that water vapor can condense into the liquid form, and it can also condense into a solid form. So this is when those gases start to condense. That is the very first step in planetary formation. And because different materials are condensing, that starts to form some different objects there. And so here in this picture here you can see we have that counterclockwise rotation, that motion, and all of these little kind of splotchy things represent condensation beginning to happen. The next step is called accretion. And accretion is growing by colliding and sticking. So this is when those solid particles start to bump into each other and they start to stick together. And this once accretion starts to happen, we call these objects that start gaining more and more mass, we call these planetesimals, and these are pieces of planets. Small planetesimals can be lots of shapes, and if you kind of think of an asteroid, that's what these planetesimals look like at the beginning. They can vary in size, so we can have some large ones, and the larger they get, the more spherical they get, because what happens is gravity pulls them in and starts to pull them into a spherical shape. In the inner solar system, it was only rocks and metals that condensed because of the temperature. Our next step in planetary formation is called nebular capture. This is the growth of icy planetesimals by capturing larger amounts of those really light elements, the hydrogen and helium. So the inner planets kind of arrest their development or stop growing after accretion. The outer planets are massive enough to undergo nebular capture. So they have enough mass that they're able to capture these lighter elements. The small inner planets aren't heavy enough to be able to capture hydrogen and helium because they're such light elements, but those outer planets are already so massive and it's so much cooler out there away from the sun that they're able to capture hydrogen and helium. And moons are also often formed this way as well. So near the Jovian planets, the material around them also formed through condensation, accretion, and nebular capture, turned into moons around the systems as well. Now, solar wind is responsible for kind of cleaning up the solar system. It's a flow of charged particles ejected by the sun in all directions, and it still happens today. But when the sun was young, the solar wind was much, much stronger, and so that wind swept out the remaining gases in the inner solar system and pushed it out towards the edge of the solar system. If the solar wind wasn't as strong, then scientists predict that ices could have condensed in the inner solar system, but it was too hot there. It was too hot near the sun and with the solar wind for ices to condense. So those ices are only in the outer solar system. So then what about all the leftover material, all the leftover chunks? Well, a lot of those ended up getting pulled into the different planets and hitting the planets and creating lots of craters. And that's why we see things like the moon and Mercury so heavily cratered, is because the planets were pulling in those objects. But the leftover ones became our comets and asteroids. The asteroids, like I said before, mostly congregated between Mars and Jupiter in the asteroid belt. And the comets were kind of, the icy bodies are out in the outer part of the solar system. The asteroids were tugged on by the strong gravity of those gas giants and got very, very highly elliptical orbits. So they don't have the circular orbits of the planets, but they have much more squished orbits. So what evidence do we have for ongoing planet formation? Well, we see this happening in other nebulas. So if we look at the Orion Nebula, we see evidence of young stars being produced. And we see here, you can see kind of a gas disk with possibly a star there in the center. So these are possibly, in these areas, are where we think planets might be forming right now. So we see this process happening in other nebulas. So when exactly did this happen? What is the age of our solar system? Well, because we're talking about the sun and the planets forming at the same time, then they would be the same age. And we can actually measure the rocks in planets to figure out their age, and this is called radioactive dating. And this is something that we'll talk about more in some upcoming units. But just a little overview, what we end up doing is taking some radioactive elements, and they have kind of a set age in which they start to decay. So we know that if it's a certain parent atom, we know how long it's going to take to decay. So if we find that in a rock, we can tell how old it is. So we measure the abundance of a radioactive decaying element to see how long ago did it form. And when we date the rocks on Earth, we see that it's about 4.6 billion years. And when we date rocks on the moon, we see the same thing. And also, most meteorites that we have found have the same age. So we figured that the solar system formed somewhere around 4.6 billion years ago. So one thing for you to think now is what could have sparked this nebula of gas and dust to start collapsing in the first place? And I want you to just think about that and come up with your own ideas. And then in class tomorrow, we'll kind of take a look at some ideas of how that might have happened.